Thanks for coming. So my name's Andrew Davison. I'm a professor in the computing department here, and in particular I am leading the Robot Vision research group and also a fairly new research group called the Davison Robotics Lab, which I'll say more about later. But I'm going to talk to you about some of the work that we're doing on giving robots a sense of vision. So just to quickly go through some basics. So if we ask the question, what is a robot? My answer would be something like this: a physical, artificially intelligent device with sensors and actuation. So physical means, it has a body, it exists. It's not just a computer program. But the really crucial things that make a robot is it has sensors, which means it has some devices which enable it to sense the outside world. And then it has actuation, which means it has the ability to then act back on the world. So it's not just purely passively observing the world. It's actually observing it and then acting back on the world. So acting back on the world could be wheels, or it could be arms, or it could be legs, or anything like that. So clearly, the tricky bit is to connect those two things together. So it's got to sense and it's got to act. In between there, it's got to somehow think and decide what to do. Maybe a good question is a washing machine a robot? Because actually a modern washing machine has sensors. Clearly it has actuation. It moves things around. And it connects those two things together via some sort of processing or thinking. But I would probably argue that a washing machine is not a robot. And maybe a nice distinction is that a washing machine's operating space, the volume of things that it's interested in, is contained inside its body. And therefore it's very well controlled. Whereas a robot, you want it to work kind of on the space outside of its body, where clearly it's much harder to control what's going on in that space. So if we think about where robots have been successful up to now, it's this class of robots. So doing things in car factories or other similar settings where essentially they're mounted on fixed bases and they're doing the same thing again and again. So these robots are successful because the things that they do are very much pre-programmed, and they do the same thing over and over again, and the whole environment is set up for them to operate successfully. So what about this kind of class of robots? So these are a number of current research robots that are aiming to go out into the wide world, so not just staying fixed in factories, so underwater, on city streets, in farms. I'm not even sure what this one is, in a mine or something. Climbing through a forest, dropping safety gear to someone who's stuck in the water, or even, exploring another planet. So if you want robots to do things like that, clearly they're not going to be able to just do the same repetitive thing. They're going to need to respond and react to what they see around them. But even though those applications sound really difficult and exotic, there are just as hard challenges in home robotics, and that's the particular area that I've been interested in for quite a long time. So consider this video here. So imagine if you had a robot that could do all of this, that could come into your home, tidy everything up, plump the cushions, clear up all the Lego off the floor, and just tidy everything up. So who wouldn't pay a lot of money for a robot like that? But you might think, okay, well, this robot seems to already exist. But actually, no, this is a fake video. So this was created at Stanford a few years ago. And actually, this robot was completely teleoperated by a human. So a human was basically controlling it with some kind of, joysticks to do what was wanted. So, for me, that's an interesting demonstration that actually, physically, we can build a robot that can do an awful lot of those things. The thing that's missing is the perception and control to actually be able to do that autonomously without having this amazing human brain in the loop to actually, control what's going on. So that's really what I've been focusing on in my research and continue to do it. So how do robots get that sort of perception of the world that they could then use to control motions like that automatically? So there's one particular key problem that I've been interested in my research, which we call SLAM, which stands for Simultaneous Localization and Mapping. And it's basically the problem of how does a robot, which is dropped into some space which it's never seen before, how does it kind of gain a spatial understanding of that space so that it could operate automatically in it. So this is really true. Whether you have a robot that lands on another planet or lands in some space underwater or just arrives in your home for the first time. So it's faced with this kind of space that it doesn't understand, and its goal is basically to make a map of that space and then estimate where it is with respect to that map. So that's the tricky character of this problem that we call SLAM, is that you're going to build a map as you go, and then you're going to estimate your position relative to that map. So localization and mapping. And the essential way that we go about doing that, and in particular using cameras as the main sensor, which is the area that I'm interested in, is we move a camera, the camera connected to a robot is moving around through a space, and it captures lots and lots of images of what that space looks like from different positions. The essential thing it's got to do is to find some things in those images that it takes of the space and say, well, okay, these things are quite distinctive. I'm going to use them as landmarks. These are things that stand out in the image, and I can find them again and again as I move around. And then basically, as it moves around, it gets lots and lots of different measurements of where are those landmarks in my image relative to my current position. So basically, an image position is an angular measurement of where those landmarks are with respect to your current position. So if you get lots and lots of those angular measurements, it's actually then possible to solve both for the 3D positions of those landmarks and for the motion that the camera must be going through as it observes them. So I'm not really going to explain too much about the detail of how we do that. But essentially, it's an estimation problem, and it's a joint estimation problem in lots and lots of different variables, because basically at the same time, we are estimating the position of the camera as it's continuously moving around and the positions of all of these landmarks. So if we're mapping hundreds or thousands of landmarks in a scene, we're estimating thousands and thousands of variables in an estimation process. And the basic way we do that is using probability theory, Bayesian methods. So we take account of the fact that every measurement that we make has uncertainty in it, and if we fuse lots and lots of uncertain measurements to get some overall picture of the world, the right way to do that is probability theory. So there's a little sort of animation here that illustrates a little bit of how that works. So we've got a robot moving through a space, and as it's driving around, there's always a kind of ellipse around it, shown in yellow, which is representing its current uncertainty in its position. So the other things you can see, these are the landmarks that it's mapping and observing. As it's moving around, observing these landmarks again and again, the uncertainty in those landmarks will gradually reduce. So it first sees something it wants to add to its map. It's pretty uncertain about its position, but if it can move around and make lots and lots of observations of that thing from different angles, different positions, it can gradually reduce its uncertainty in where that thing really is. So this is this basic procedure of probabilistic SLAM, and this has been actually implemented by a lot of different researchers on a lot of different robots, and in particular using a lot of different sensors. But the thing that I was really interested in, and this is now more than 10 years ago, is could we do this basic thing of SLAM using just a single camera and nothing else? So that's really interesting, because if you could do it in that really general way with a very cheap sensor, a single camera is now something that's, all of us have them in our pockets probably, they're everywhere, they're cheap. If you can do this basic thing of localization and mapping with that sensor, you can apply it to a lot of different things. So we managed to get some first solutions to that. This is now, about 10, 12 years ago with a system called MonoSlam. So here's the setup. It's a handheld webcam, so this is just a standard cheap webcam, and it's connected to a computer. And there's nothing else. There's no other special sensors here. There's no kind of infrastructure in the room. And so we're going to move the camera around the room. It's handheld, so there's no robot here, but we're moving the camera as if it might be connected to a robot or something else. So this is basically what the camera sees. As the camera's flying around, it captures video at 30 frames per second, and then you'll see that it's identifying these landmarks that I mentioned. So these might just be the corners of posters or objects in the room, but these are things that stand out from their surroundings, and they're things that we can track as the camera moves around. You see that it's finding new ones as it moves into new spaces. As it keeps moving, it's always searching and finding the same landmarks, and this is visualizing something about how it searches for landmarks within these small elliptical regions And that's one of the things that makes this whole system run quite fast. And then this is the basic output of that algorithm. So it's a real-time estimate of the 3D position of our camera. So this is shown as this grey box that's flying around here. So every time the camera captures a new image, we get an updated estimate of its 3D position and orientation, which we then display in this video here. And then the other things you can see are the estimated positions of the landmarks. So each of these has a little texture patch which uniquely identifies it. And then it has this 3D elliptical region, which is the uncertainty in its position. So again, we see this character that when we first see new landmarks, they have big uncertainty. When we measure them many times, that shrinks. So this was an early demo of something we could do with that. So, we'd been interested in robotics, but as soon as we implemented this, we realized actually this is probably useful for other things other than robotics. And one is augmented reality. So this is something you may have heard a lot about. It's the basic process of trying to take real video and combine it with virtual augmentations. So here we thought, could we make a demo where we're going to put virtual shelves up into a real room? So we've got a camera flying around, it's capturing this video, and on top of that video, we want to put shelves that look like they're really kind of stuck to the real world. So the way to do that is we take our pose estimate that's coming out of MonoSlam, and we feed that to a graphics engine, OpenGL, and say, draw shelves as if from that point of view, and then put them on top of the real video. And then if your tracking of the camera, your SLAM is working properly, you get this nice effect where the shelves really look like they're stuck to the real world. So this was quite a few years ago, and you can see some of the imperfections in this, but the fact that this was running in real time was really quite interesting. So we realized, as I said, if you can do this with just a single camera and no other sensors, you can do quite a lot of other different things with it. So basically, without needing to change any of the software, you can run it, for instance, on a humanoid robot. So here we're using a camera in the robot's head. So I don't actually show the result here, but we track its motion as it's driving around in the room. Another interesting setup here is an early work on wearable cameras. So this is something that's really come back into vogue in the last year or two with things like Google Glass, which you've probably heard about. So here's a camera mounted here on the shoulder, which as he moves around, we've got the MonoSlam algorithm running on the video from that camera, and we can track its position and therefore estimate the motion of the robot that's moving around. So most interestingly, technology that's really very much similar to this has now become part of this real product called the Davison 360i robot vacuum cleaner. So I'll just show some of the video. It's very, very slick, as you'll see. So this is a product from Davison, which I worked on as a consultant for about 10 years to basically figure out how we could get this mapping and localization technology to work in a real product. So this is going to be on sale in the next couple of months. So this robot has an omnidirectional camera. So that little bubble in the top is a camera which captures an image that looks something like this. So it's not just a standard picture. It's a 360 degree strip that goes all the way around. But then what we do with that image is very much the same as what I've shown you before. The camera is finding and tracking landmarks. You can see some of them visualized. Here's a kind of external view of the same thing. And then because it's tracking those landmarks, it can do this SLAM processing and basically estimate where those landmarks are in 3D and estimate its own motion with respect to the landmarks. So what that enables is this kind of precise navigation. So if you've seen any previous robot vacuum cleaners, a lot of them basically, to try and clean your room, the plan is to bounce around it randomly for a long amount of time. And that's actually not a bad strategy. You'll find your way into a lot of corners eventually by doing that, but it's relatively inefficient, and you'll end up crisscrossing certain areas many times and maybe missing other areas. Whereas because we're doing SLAM, we've got a map, we know where we've been, where we haven't been, and therefore you can clean in this very efficient manner and then come back to the base station to charge up again when you're finished. So that's been really, really exciting to be involved in that project and to see it come all the way through to fruition. So let me just show you a few more things. So basically that research has moved on an awful lot since the systems I've shown you there. So a nice one to show you here. This is work from Raúl Moore, who's from the University of Zaragoza in Spain, who's currently visiting our group here at Imperial. He's made a version of this monocular single-camera SLAM that can now work really very effectively from just video and no other information on huge-scale outdoor scenes. So this is a setting which might be applicable, for instance, to autonomous cars type of setting. So you'll see that some of the things that are different from what I've shown you before, just the scale, the number of landmarks we're talking about here is now in the, I think it must be tens or hundreds of thousands. The scale of the trajectory is on the level of kilometers rather than a few meters. And you'll see that we're making, really large-scale consistent maps here. So something nice happens here, which is called a loop closure. When he comes back, the system realizes actually that it's in a place that it's been in before, and we should see a kind of snapping, loop closed, where the map kind of corrects itself. So after going around a long loop, some incremental error has occurred, but when you recognize you're back somewhere you've been before, you can correct that error with an optimization. So, yeah, I mean, there are various dimensions along which we've improved the performance of those early visual SLAM systems in the last few years. But I think the one that's been most exciting has been thinking about how to really improve the level of detail that we can reconstruct. So whereas we were mapping a room at the level of a sparse set of landmarks, tens or hundreds of landmarks, what we've been able to move towards recently is mapping a room at the level of thousands or even millions of vertices. So what that has really been enabled by is the rise in commodity computer power. So these are some curves. You've probably seen similar ones showing a comparison here between basically the year on the horizontal axis and basically the peak computer power, so measured in gigaflops here. How many operations per second can that sort of processor do? And something that really interesting that has happened recently is that the classic single-core processors, so these ones down at the bottom here, which are basically like an Intel-style CPU that you have in a PC, those are still going up, but gradually getting sort of slower. Whereas if you compare that to this curve here, these are the NVIDIA range of graphics cards. So these are big processors that are originally designed to enable very efficient graphics for computer games. A few years ago, it was realized that you could use those as general-purpose, massively parallel computers and apply them to all sorts of mathematical computing problems, including computer vision, that they're really well suited to. So this gives you a lot more processing power to work with, but it can be harder to use because you can only use it with certain sorts of algorithms. You have to have algorithms that are parallelizable to be able to use this compute. But the sort of algorithms that I mentioned, which are about adding detail to our reconstruction, are perfectly well suited to taking account of that. So this is some work from 2011 by Richard Newcomb and Steve Lovegrove working in my research group. So this was a system called DTAM, where what we're doing now is mapping not just a few sparse features in the scene, but basically mapping, trying to estimate the depth of every single pixel in an image. So it's basically the same kind of input as we had before. It's a single camera flying around a room, but we're trying to build a map now which is completely dense. So I'll show you some of the pictures later on which really show you what that means. So as we're moving around, you'll see here that we're reconstructing this level of detail in the scene. And that's enabled by algorithms which are matching not just these kind of landmark high texture points in the scene, but trying to match every single pixel in the scene. So that requires a certain sort of global optimization algorithm, which it is possible to parallelize very effectively on a GPU. So this is really interesting to us because going right back to some of the things I showed you earlier, in robotics, we want robots ideally that don't just know where they are, X, Y, Z. Like for a robot vacuum cleaning, that's enough. But if you want a robot that could actually do something like clear a table, it needs to have a detailed 3D understanding of the scene around it. So this seems to give some promise of doing that kind of thing. But, as before, we can do other things with it, which are maybe more immediate and fun than robotics. So, for instance, we can return to this augmented reality problem I mentioned before. So this is, again, this problem of putting virtual things into real video. So here we're going to put a virtual car into this real video of a desk. But now it's not just going to sit in one place, like a shelf pinned to a wall. We're actually now going to drive the car around on the real surface of the world. And we can only do this because we've reconstructed the shape of the real surface in the world. So hopefully this might lead to quite fun sort of games in the future. So something very closely related to the work I showed you before is a system called Kinect Fusion, which was done in collaboration with Microsoft Research and became very well known. So this takes advantage not only of GPU processing power, but also novel things that are going on in sensors. So there are new types of cameras. So this is something you may often have seen at home. It's the Xbox Kinect camera that came with the Xbox game console. And this is actually, a really amazing sensor because it captures not just color images, it also captures depth images. So that's enabled by a structured light system where it projects an infrared dot pattern on the scene and observes it from a small offset. So this actually gives us quite a shortcut to 3D information, which you can see is able to now very kind of efficiently and robustly do 3D mapping. So, a single Kinect image looks something like this. It does have this depth information, but it's noisy and it has holes. But by applying SLAM algorithms to it and basically fusing lots and lots of this noisy information probabilistically into a single model, we can get a nice, smooth, and complete model that looks something like this. So this is very much the sort of technology, vision technology, that we're now interested in applying to problems like robotics. So actually, in the very first Imperial Festival in 2012, we were demonstrating this technology and using it to reconstruct people. We also did some, 3D printing of the shapes of people. So this is my head that you can see we've scanned using this Kinect Fusion system. So actually, what we can show you just now is something that's very current. So if this is Tom Whelan, who's one of the postdocs from my group, just comes to help me for a second. So we need to. So this is a new system called Elastic Fusion, which is really an improvement on what you just saw there, Kinect Fusion. But the goal is still the same thing, to do dense mapping from a handheld camera. So this is a camera which is very similar to the Microsoft Kinect sensor. It's a depth camera. It captures a stream of depth images at 30 frames per second. Do you want me to hold it? And basically, you can see that as we pick up and move this camera around, we're building incrementally this really high quality and detailed 3D model of the world. Should we try it over here? Let's try it over here, with these characters. So what this map is actually made up of is thousands or eventually millions of tiny little disks, which we call circles. So each one of those circles is a little oriented disk that has a 3D position, it has an orientation, and it can also have a color or other attributes. So in fact, if you go outside later on, you can see we're running the same reconstruction system on a camera that's attached to a robot arm, which can be moved around. But you can see that compared to the sort of SLAM that I was showing you at first, where all that we knew about the world was the location of 100 points in this room, we're now capturing, immeasurably more information here. So if we think, our goal now is to try and build the sort of robots that could really interact with this scene, I think you can get the idea that we're now starting to get the kind of level of information that might make that realistic. Okay, thanks a lot, Tom. Go back to PC. Okay, so there's a couple more things that I'd like to show you. So, knowing about the geometry of the scene in that really dense way is clearly really important, but it's still, it's not everything that a robot needs in order to be able to do intelligent things. So a robot that needed to clear a table, for instance, would need to know not just about, the detailed shape of things, it needs to know what things are. So it really needs to know, okay, that's a cup, that's a teapot, that's a fork, and then that's the way to pick those things up, and this is what I need to do with those things. So we've started to do some work on SLAM that can actually understand objects. So this is, a very active area at the moment in computer vision. So the particular area that approach we've taken first, we made a system called SLAM++, which is about building a SLAM map directly at the level of objects. So basically this says we've got this pretty much the same setup. We're coming into a scene with a handheld depth camera, and we want to make a map. But we've got a bit of extra prior information, which is that we are aware that this set of objects are likely to exist in this scene. So this is a fairly small set of objects we have here, but this works really well in an environment like this. So this is a kind of coffee room where actually there are dozens of chairs of exactly the same type and dozens of tables of exactly the same type. So as we run the system, we move the camera around, and then we have an object detecting module that's looking at the 3D shape of lots of these points, and it's trying to fit 3D object models to those points. So again, here's the raw Kinect data. This is the color image, which we don't use, but then here is our reconstructed model. So as we detect instances of these objects that we know about, we start to populate our SLAM map with them. And then behind the scenes, we've basically got our SLAM estimation framework going on, which is taking now lots and lots of observations of, I saw this chair from this viewpoint and measured that its position was like this. And then I saw it again from this position and measured that its position was like that. So we fuse lots and lots of those uncertain observations to then build a coherent 3D model of where, what the layout is of all of those objects in the scene. So, this is still quite limited in many ways. It's, it's only a pretty small set of objects that we're dealing with. But I think this is showing us some sort of promise of dealing with, scenes with objects in them. So we can return to this augmented reality thing I've often mentioned here, and do an even more interesting version of augmented reality, where we can do kind of automatic object-aware augmented reality. Let me just find the right place. So in fact, this is what we were demoing at the Imperial Festival 2 years ago. So basically, because we recognize those chairs in the scene, we can add a virtual character to each one of the chairs and make them sit down in it, because we know that chairs are things that people should sit on. I'm not sure whether people really understood what was going on here, but we had a lot of fun. It's quite subtle. So something related to that is a system called Dense Planar SLAM, which we just published last year. So this is showing how, as well as identifying objects, another thing that's easy to identify in a scene are planar regions. So we've got this map consisting of millions of these circles. If you have objects like the top of desks, the front of fridges, all the circles there tend to be very closely planar. So you can fit planes to those and then explicitly recognize which are the different major planes in our scene. And then you can have nice effects like this, where you can, this is a cool one, where once you've mapped an area, you can use it for a display of information. Sorry, okay. So we're moving the camera around. This could be a camera which is attached to something like an Oculus Rift virtual headset. So I think this is really looking forward to the sort of future of see-through augmented reality. So he's moving around, he's got the camera on his head, and he makes this planar level map of the scene. And then he's put his Facebook wall on a real wall. So Imagine if you want to, display information as you're browsing around through the real world. The obvious way to do it might be just to have some drop-down thing that appears in your field of vision. Actually, that's not a very pleasant experience. Why not sort of attach that information to a real surface in the wall, and then you'll have a much more natural effect. Or you can do fancy things like change the texture of the carpet and see what that looks like. Okay, so something I've been thinking a lot about recently is, putting a lot of this research into context. So these are some of the systems that I've worked on, starting from my PhD work back in the late 90s through to some of this more recent stuff. I mean, it's obvious to me that we've seen, a massive improvement in what we can do. And, some of that is through algorithmic cleverness. I think an awful lot more of it is through to just rising computer power that allows us to do more and more. And I think it's interesting to compare that to this general, flow of technology where you forget how fast all of these things have happened. So, for instance, YouTube didn't exist about 10 years ago. It's hard to get your head around. Or even, digital cameras, mobile phones, you weren't really aware of them until the mid to late 90s. So technology is moving incredibly fast. That makes me think. And, you start to think, well, what might be happening in the future? So very clearly we can predict, I think, some things that this sort of technology we're working on here will enable in the near future. So I've mentioned robot vacuum cleaners. These are some of the ones that already exist. This shows clearly this quite kind of random movement pattern of some of the existing models. So we're working closely with Davison in particular on future robots for the home. So this is the robot I've already shown you. This is a prototype actually that Davison got very close to releasing. Actually over 10 years ago, before I was ever involved with working with them. It was actually a very nice robot, but I think they made the decision in the end. They weren't quite ready. They weren't sure they were going to make a profit on it. But it was very advanced for its time. But what we're really working on now, so the lab that I'm leading now here at Imperial, the Davison Robotics lab, is we're really trying to think, not just how can we do more with vision on things like robot vacuum cleaners, but what's the research we can be doing now that will hopefully lead to the next generation of robot products for the home that could really be useful. So this dense 3D mapping is very much a part of that. And then, as I mentioned, we're already starting to work on manipulation. So you can see the demonstration outside where we have one of these robot arms carrying a camera, and we're starting to think about those difficult problems. Another big class of products, which I think is certainly coming soon, is this SLAM technology working on mobile devices. So you may have heard of some projects from big companies that are now invested in this. So Google, for instance, have a project called Project Tango, which is about basically putting SLAM into a smartphone class device. So this is hard because you need a lot of computer processing. You need ideally you can do SLAM with a single camera, but if you can fuse some information from other sensors like inertial sensors, it's a lot more robust. But really, how do you run on that small, cheap processor that can fit in something like a mobile phone and not use too much power? That's the really tricky thing. And there are other very cool projects. One announced just earlier this year, Microsoft HoloLens. They also have a very high-performance sort of headset, which is clearly doing SLAM as well as other things. And then 3D scanning, I've already mentioned. I would be very surprised if within, I don't know if it's going to be 5 years or 10, every grandmother in the world doesn't have these kind of 3D printed models of their grandchildren on the mantelpiece. I mean, the technology's already there. Someone's just got to commercialize it in the right way, I think. So there's this kind of, view of how technology is going. What about even further ahead in the next 10 years? These are some of the things that I'm really motivated to work on. So, really practical real-time scene understanding that can work on embedded platforms like smartphones, like small robots. And clearly all these devices should be, not independent. They'll be communicating through the cloud. And I think we can strongly expect that there will be kind of real-time 3D maps of the whole world, which are built collaboratively by everyone moving around with their smartphones and other devices. So, for better or worse, or whatever that will enable, the technology will enable that, I think, quite soon. So I'm particularly interested in getting back to, really an active use of computer vision and robotics, so manipulation of complex objects and scenes. So that's still staggeringly difficult. I think anything you've seen of robots that actually pick things up and move them around, generally done in very, very controlled settings. So the state of the art in having a robot just come to a table and do sensible things with the objects on it is still pretty hopeless. So I think we're going to be working a lot on that. I'm also quite interested in, so I say here, return to biologically inspired methods for their low power requirements and robustness. So, a lot of the work that we've been doing, or all of the work we've been doing really, has come from an engineering viewpoint. We want to make things that work. We haven't necessarily worried about whether the vision systems we're building have any biological analog, whether they have anything in common with how human or animal vision works. But they're working, and they're working better and better. That's what's interesting. But, you do remember every so often, actually, there are still things that, the human vision system is very robust, and it can deal with a lot of things that our artificial systems can't. So just some hints of things that are related to that. We've started to do some work in the last couple of years with a new type of camera that's called an event camera. So this is a camera. Currently you can buy it as a research prototype. It costs about £1,000, but it doesn't capture full frame images. Instead, it captures differences. So every pixel is a kind of independent, asynchronous change detector. So as we're moving the camera around, you can see that in the right here, this is a visualization of the events. So every white dot is a pixel saying it's getting brighter. Let me just go back to that. And every black dot is a pixel saying it's getting darker. So what we're starting to do is think about how we would do SLAM with that kind of sensor. And we've got some first results here showing that we can go from that event data to actually a reconstruction of something that looks like images that a normal camera would capture. And that requires using that stream of events both to track the position of the camera and then to reconstruct a mosaic of the scene that it's seeing. So it is basically a SLAM sort of processing that we're doing there. And we want to continue from this into doing generic 3D SLAM. So that's interesting because this camera seems to have a lot of advantages. It has a very low data rate, for instance. So compared to a standard VGA camera, I think it's on the order of 10 megabytes per second of data coming off that, whereas the data from a camera like this is more like 10 or 100K per second, because it's only telling you about differences. It's not again and again saying this pixel's white, this pixel's white, this pixel's white. That's basically what video is sending to you again and again. It's only telling you when something's different. And also it has advantages of being able to track very, very fast movements because each pixel is independently clocking itself and it runs at sort of microsecond levels, and also huge dynamic range, meaning it can deal with scenes that have a very wide range from dark to bright. So again, maybe a bit like the human eye. So we're starting to look at algorithms like that. So, I have this view of accelerating technology, and you wonder what that's going to lead to in the future in terms of, is this technology going to overpower everything? So that's something I have different views on each day of the week when you might ask me, but always interesting to discuss. Anyway, that's the end of my presentation, so thank you.